Hello, good day, guys. My name is Faith Olasende. It's nice to meet you guys again after a long time due to the strike. Yeah, by the end of this tutorial, you will have covered how to sharply get the hybridization of any compound. Yes, and I mean the shortcuts. I'm your dear shortcuts master. What else are we waiting for? Let's get right in. What is hybridization? Hybridization is simply mixing of atomic orbitals of different energy levels to form molecular orbitals of identical energy level. Okay, I know I might be saying something strange.
This is not okay. This needs to stop now.
But let's break this down.
Nice.
In order to break this down, let's go way back to electronic configuration because I'm quite sure I never covered it in this channel. Atoms have electrons running around its nucleus. In order to be able to tell how electrons are placed around the nucleus in different levels, then we are talking about the configuration of the electrons, hence electronic configuration. They can be configured using key element or the SPDF configuration. The key element configuration defines the shells of the atom and follows the formula 2n square. This means the first shell is K and it is number 1. So using the formula, it equals 2 open bracket 1 raised to the power 2, which is 2. It means only 2 electrons can exist in K shell. However, for the L shell, which is number 2, by the way, it goes 2 open bracket 2 close bracket square, which is, by the time you calculate, it's 8. And the next one is 18, if you calculate it, and it goes on and on like that. And if there is need for it, I'll make another tutorial to fully explain this. Now, the SPDF configuration goes to the next level by defining the orbitals in the shells. In each shells, we have orbitals. There are 4 main types of orbitals. Well, at least that's what we know so far. Anybody can come up tomorrow and say we have 6. Well, so the 4 are s orbital, p orbital, d orbital, and the f orbital. The s orbital can hold 2 electrons, p orbital can hold 6, d orbital can hold 10, and f orbital can hold 14 electrons. Each orbitals can be broken further into their degenerate orbitals, that is, suborbitals, and that means little orbital in those orbitals. Each degenerate orbital can only hold 2 electrons. That means s orbital has only 1 degenerate orbital. Then p has 3 degenerate orbitals, d has 5, and f has 7. If you look at it closely, it means K shell is on energy level 1 and can only hold 2 electrons. Then it holds just the s orbital, and that means it's just 1s. L shell can hold 8 electrons. That's a combination of s and p, and s is 2 and p is 6, so that gives 8. It means at the L energy level, which is 2, you have 2s, 2p, and it goes on like that. For K is 1s, for L is 2s, 2p, for M is 3s, 3p, 3d, and so on. Where am I driving at with this for the main topic, which is hybridization?
Go and ask your grandfather.
When hybridization occurs, it involves the SPDF orbitals, which results into covalent bonds. That's why I took time to explain the electronic configuration. And how does hybridization occur? Take carbon compound as an example. The atomic number of carbon is 6. Using the K element configuration, you get 2, 4, 2 electrons in the K shell and 4 in the L shell. But using the SPDF configuration, you get 1s2, 2s2, 2p2. We all know most atoms are naturally unstable. They always want to bond to achieve stability. And atoms are stable in two states, the octet state and the duplet state. The octet state is when the outermost shell has 8 electrons. The duplet state is when atom loses all it has in the other electrons or accept in order to retain the K shell with just 2 electrons and be stable. In order for carbon to be stable, it needs 4 more electrons to add to its shell. In order for this to happen, carbon must be in excited state. This will allow mixing of the orbitals in the L shell, which are the 2s2 and the 2p2. Remember that we can break them into their degenerate orbitals. In the end, you get spp on energy level 2. Due to the orientation of the electrons in the orbital, the p orbital are labeled px, py, pz. One pair is oriented towards the x, the other towards the y, and the last towards z. But carbon has 2 electrons in the s orbital and 1 in the first 2p orbital. The p orbital is quite higher in energy level than s orbital. Therefore, there is need for mixing of those orbitals to bring them to the same level. When carbon is excited, the electrons will redistribute according to the Hund's rule, that electrons fill singly in each degenerate orbitals before pairing occurs. When carbon is excited, this orbital mix to form 4 sp3 orbitals with the same energy level. That's why carbon can form 4 bonds with hydrogen to form methane or probably any other compound. The bond formed by overlapping of hybridized orbital is called the sigma bond. There are many types of hybrid orbitals. We have the sp orbital, which is formed by the mixing of s and p of an atom to get the sp hybridized orbital. Take beryllium 2 chloride for example. Beryllium has 4 electrons, and that's 1s2, 2s2 and 2p0, right? Naturally, beryllium should lose 2 electrons in its outermost shell and be stable, but beryllium has high ionization energy and would not form ionic bond, it would rather form covalent bond. And how does this happen? Beryllium gets excited and the orbital in its outermost shell mixes. Because it has just 2, it then spreads to just 1 p orbital. Therefore, it forms sp hybridized orbital. That's how it applies to sp2 hybridization as well. What happens to carbon in 18 C2H4? After being excited within a particular environmental condition, carbon only mixes 2 of the p orbitals with the s orbital, forming sp2. It means that 1 p orbital is left unhybridized. The unhybridized p orbital overlaps with the other unhybridized p orbital of the carbon to form a pi bond. Remember, we have 2 carbons in C2H4. So the overlapping of the unhybridized orbital of the 2 carbons form the pi bond. This pi bond is the one responsible for the double bond that appears in the compound. So now, the shortcut that you've been waiting for. How do you quickly determine the hybridization of any compound given to you in text or exam without having to draw out before you can get the answer? It's quite simple. It works for 80% of the questions you might come across on this topic, and 80% is a pass, right? For example, what is the hybridization of BEF2? What you need to first do is check the subscript. Subscript here is 2. It means sp. What you just have to do is spread the number across sp3d5f7. The subscript here is 2, so 1 goes to s and the last one goes to p, so that's sp. Let's check CH4. Now the subscript here is 4, so it means you just spread the 4 across sp3d5f7. 1 out of 4 goes to s, then the remaining 3 goes to p, since p has the maximum of 3, so that's sp3. Let's check SF6. By the time you spread 6 across sp3d5f7, you get sp3d2. 1 goes to S, 3 goes to P, and the remaining 2 goes to D. Like I said, it works 80% of the time, but just like in real life, some don't follow rules. For example, SO2 should be SP, right? But it is SP2 for some weird reasons that I cannot start explaining. Water as well, H2O, is SP3. I would advise that you know those compounds that don't follow the rules. Well, that brings us to the next question you get in exam. Sometimes you see questions like, how many sigma bonds do you have in CH4? Remember I said pi bonds are formed by overlapping of unhybridized orbital, forming the double bond or triple bond. The overlapping of hybridized orbital forms the sigma bond. Since CH4 does not have double bond, then it does not have any pi bond. Then it has just 4 sigma bonds. What of C2H4? 18. In this case, you have 5 sigma bonds and 1 pi bond. And you count them, you have 1, 2, 3, 4, 5. And the last one here is the overlapping unhybridized orbital of the 2 carbons. And that's the only pi bond. The same goes for C2H2, which has 3 sigma bonds and 2 pi bonds. I hope it is well understood. I remain on that side of faith. Until next time, bye.